Now, welcome Fab Lab Network, and welcome to the last recitation of an amazing season. And we are very lucky to have this closing recitation with Carl Bass, CEO of Autodesk, a very empowering company for all the network. And I leave you, Neil, to make the intro. And thank you, everyone, for joining. And of course, thank you, Carl, for being part of this.
Great. So I'm delighted to have Carl join us for the last recitations. You're no doubt familiar with Autodesk. They're a great friend of the maker movement from the beginning. They've been a great supporter of the Fab Foundation. I think my favorite thing Carl did was, I guess about 2 years ago now, he declared Autodesk software to be freely available for education, nonprofits, and startups. And I was talking to him about that, and his answer was amazing. It was like, how did you justify that? Because he took a lot of money off the table. And his answer was that if machines make machines, and this is spreading virally, the software needs to be available. And it wasn't really clear who pays whom for what and how it plays out, but this was the right thing to do. And they would kind of catch up later. And so I know his staff was screaming at him over it. But it was the right thing to do, and you sort of do it and you figure out as you go along. And so it was a really amazing thing he did. And so with that, I'm delighted to hand off to Carl.
Thanks, Neil. I'm thrilled to be here. Somebody's got an echo on. Is that you, Thomas? Okay, that's much better. Hey, I'm thrilled to be here. And yeah, Neil, you're right. One of my most successful things was turning a $100 million business into zero, because it was the right thing to do. But what I'm here to talk about this morning really is the future of making things, and some of the stuff I've done and some of the stuff Autodesk done. And so let's just start by looking at what Autodesk does. Some of you may not exactly know. And so next slide. So if you look at what Autodesk does, we really make software for designers and engineers and architects, and we do it, and we really do it for a handful of industries. One is for machine design and product design, cars and planes and most of the stuff you see around you. We also make software that helps design built infrastructure, so roads and bridges and all the buildings you see around. And the one people sometimes don't know about is we make software that lets people make video games and movies. And almost every movie and video game you've ever seen or played actually has used our software to create it. In addition to what I do at Autodesk, I've been making things personally for a long time. And so if you go to the next slide, I've been building things. I've built boats, I've built sculpture, I've built houses, lots of furniture, and generally speaking, I see almost every opportunity when someone wants something as a chance to build something, as opposed to go to the store and buy it. As a matter of fact, if you look at the lower right corner of that slide, there's a black granite bench I made that was carved out of a single slab of granite. That all started when my wife asked me whether we could get a bench for the garden. And I think she was intending that I ran down to Home Depot and got one. And instead, 9 months later, there was actually one that was carved by hand. So I always see an opportunity to make things, and I find the thrill itself in the making of it. In the designing and the solving problems and making. Let me turn to most recent thing I've been working on. Next slide. This started a few years ago with my son. He was probably 15 at the time, and he said to me, "How about we build an electric go-kart, Dad?" And so we started to build an electric go-kart. He built this. He was 15. He just graduated high school yesterday.
Sorry, I'm going to interrupt. Tomas, can you click present to everyone? Not everyone is seeing Carl's slides. Go ahead, Carl.
Okay, good. So Willie went off and he designed and he built this go-kart. What we've been doing recently is a friend of mine, Chris Anderson, who runs a drone company called 3D Robotics. Chris came by with his kids to drive the go-kart. And we were driving the go-kart, and then we were filming it with a drone. And afterwards, we were sitting around and we said, how about instead of just having the drone chase the go-kart, why don't we make the go-kart autonomous? So we've just spent the last few months, and we transplanted all the electronics from the drone into the go-kart. And so now the go-kart drives autonomously. And so this is an electric go-kart that drives at about 60, 65 miles an hour. And now it's driving autonomously. So we have like 400 pounds of metal and batteries running around. Even last weekend, we just took it up to a racetrack and we tried it out. This would be a good. There's a good lesson in here from my professor Neil, in that it did great for three runs, and on the fourth run, in 95-degree heat, the motor totally burned out, the magnets delaminated, and it shattered the case, and we ended up having to be towed off the racetrack. But the first three runs worked fantastically.
Carl, you should know my favorite project from the How to Make class at MIT last fall was a high-torque electric go-kart. But unfortunately, we had to shut down the testing at the open house when campus safety was worried it was going to go shooting out the window and into the river.
Well,
so
it's not a bad thing, because in the building of this, only once did it crash, but when it crashed, it was nasty.
Just a footnote: how many watts or how many amps?
The motor's like it's about 20 horsepower.
Okay.
So, anyhow, it was actually totally fun, and the idea of like transplanting the guts from one thing to another was really kind of fun. And so this has been a great project, and we're continuing to work on it. So one of the things is when we started it is Willie had really never built anything of this complexity, and so it was interesting to watch. And when I think of Fab Labs and Fab Academy, what I saw happen during this process was incredible. He went from this thing which was just an idea to where he was actually able to make it. And Neil, you probably see this with your students all the time, but he just had this idea. We didn't know the first thing about go-karts, and then a couple months later we had a running go-kart. And what was interesting was to watch the process, and he did two things. One is we built lots of prototypes and lots of mocked up things out of cardboard and plywood and sheet metal, and we actually simultaneously designed it in CAD. And so we went back and forth between the two. And we were very fortunate. We had access to a great shop down at Pier 9. And for everybody who thinks 3D printing is a wonderful rapid prototyping mechanism, what I found is that a water jet and a MIG welder were really a great rapid prototyping thing. And so we spent a lot of weekends down there with one of us running the water jet and the other the welder, and back and forth until we had a go-kart that really worked. One of the things we did, and Willie did at the time, was we designed it in a piece of software. And so if you go to the next slide, one of the things I want to talk about is one of the pieces of software that I think was great for the go-kart, but is also fabulous for Fab Lab and Fab Academy, is we at Autodesk, we designed a new piece of cloud-based software called Fusion. And the basic idea behind Fusion was we increasingly saw people wanting to go all the way from designing through running machines. With the increase of microprocessors running all kinds of CNC machines, what we saw was a really broken process out there. That the CAD software didn't talk to the CAM software, didn't talk to the analysis software. Any of you have had that experience, you know how frustrating it is. Something happens, you got to start over, and none of it really flows the way it should. So we said we wanted an easy-to-use cloud-based piece of software that lets you go all the way from designing through fabrication. And so we designed this piece of software. If you go to the next slide, you can see some of the people who are using it, used around the world at schools. We have hundreds of thousands of users out there. If you go to the next slide, there's a great gallery, which is one of my favorite things every day. Is I get an email with all the new projects that have been added to the gallery. So go to the next slide. You can see some of the work there. It's up on the web, and there's just an amazing collection, and dozens of projects are added every day. And at the end of the day, I love just seeing the new things that have been designed. I recently just put one in there that was a table that I had made, but it really shows the full range, all the way from purely mechanical to things that are much more organic and sculptural. And that's really one of the strengths. One of the things that we thought was really difficult was the need to use 3 or 4 or 5 or 6 pieces of software to get your job done. If you go to the next slide, you can see some of the things that are already included with Fusion. One, like I said, is the ability to model organic or more sculptural shapes with the more prismatic things that you commonly see in solid modeling. Also the ability to do analysis. So finite element analysis and computational fluid dynamics built in, and you can go back and forth and make changes. And then the last thing, if you look at the next slide, which is in some ways as a maker, you'd appreciate this from me, is the ability to generate instructions for all kinds of CNC machines. Starting with, kind of subtractive machines, but 3D printers, as well as water jets and lasers and plasma cutters. And the idea is we want the fabrication and the techniques to stay really close to how you actually design it and not have to output to a million different file formats and translate and lose data and lose the associativity. We want the things to stay connected all through the process. And so we've done that. And go to the next slide. You can see available on a variety of devices, runs on Macs and PCs. The browser version comes out this fall. And also, you can look at all your models and designs on your phone or your iPad, Android phone. So it kind of works from everywhere. And the basic idea was not only to design, but so many projects these days are done in groups. And so the idea was to be able to enable a group to work together by, in that same way that you know what's going on in social networks. This way you know what's going on with your project, and you can see updates and you can work together in a way that the more traditional older tools never imagined we would be working together. So real collaborative designing and sharing and building of stuff. The good news is, as Neil said, if you go to the next slide, is that Fusion is free for students and faculty and institutions. It's also free for startups, and it's free for makers and enthusiasts. So you can go up to the website, you can download, and anybody can try it and use it as long as they want. So that's my little pitch for Fusion, which I think is perfect for the maker community. Let me just spend a few minutes, and then we can do a little discussion in Q&A, talking about what I think is some of the most interesting trends going on in the world of design and engineering and software that drives it. So go to the next slide, please. So the thing I've been thinking about and we've been working on is a handful of years ago, it became clear to us that one of the biggest trends out there was the falling cost of computing power and the increased availability of computing power on demand. And, if you think about it, you can rent a CPU these days for about 2 or 3 cents an hour. It's almost the cheapest thing out there you can rent. And it's going down in price, and predictably so, and it's one of the cheapest things you have to solve any problem. Yet, when you look at most people who design and engineer things, they often treat computing as though it was kind of scarce and precious, as opposed to it's abundant and cheap and almost infinite. And so we said to ourselves, if you had infinite computing power, how would you design and engineer things differently? And so one of the things we looked at was this idea, next slide please, that we called generative design. And what we saw was the process of design was often one of, doing things sequentially. Having an idea, trying it out, having another idea, trying to fix it slightly, and incrementally walk towards a solution. For those of you who are old enough to remember, it reminded me a little bit of the game of Battleship, where you would go B3, and then you would test it, and it would be miss. And then it would be E5, and it would be miss. and you realize that there must be a better way. And so at first we started saying, rather than testing all these things sequentially, why don't we test it in parallel? And that certainly was a better answer to the problem. But then what we said to ourselves is, what if instead of just, kind of proposing and disposing, or proposing and testing, what if instead we let the computer, we gave it instructions to find, we gave it the specifications we wanted. We started to describe the outcomes rather than talk about the geometry or the thing itself. We described what we wanted the thing to do. And so if you look at the next slide, this is a picture of a heat exchanger. Next slide, Thomas. Maybe not. There it is. This is a picture of a heat exchanger that was actually designed by the computer. And I think this is one of these incredible things in that you have a nearly optimal answer to an engineering problem, and I think the thing is beautiful at the same time. And so what was interesting about this is nobody ever sat down with a CAD system to just draw this thing. Instead, we described things like the space envelope it could fill and the thermodynamic requirements, and this is the result that came from the computer. If you go to the next slide, you can see a similar thing that we did. This is actually, they're going to switch to a video here. So this is a little video that we did along with the folks at Airbus, in which what we did was they wanted to imagine what aircraft would look like, 30 to 50 years from now. And you ended up with something that was very different because rather than relying on the technology that had come from pressure vessels and submarines with wings on them, they actually went back and from first principles, by specifying what we needed to have happen, the computer came up with a design. But the thing about commercial aircraft is when you make something for it, it's not like a go-kart. You can't just go into your backyard and try it. It takes years and years. So we started with Airbus, and instead we did a little project on one of the bulkheads inside the airliner to try this idea. Could we just specify it? And what we did is we specified to this this tool we have called Dreamcatcher what the requirements were for the bulkhead, what shape it would fill, the mounting holes, the seats that would get mounted on it for the flight attendants, and it actually generated. And so if you look at the next slide, you can see the partition that I'm talking about. And there's the partition. And if you go to the next one, you can see the one that was actually done out of 3D printed metal parts. So rather than the composite one that's in place today, this is the one that was designed by the computer. It's just as strong as the original and weighs half as much. And in the world of commercial aircraft, reducing weight by that much is a substantial benefit. So right now, this part has been tested under 9G loads. It is going to go through a 16G test this summer. And if all is good, this will be the largest assembly of 3D printed metal parts to fly in a commercial aircraft, and it should do so this year. Neil can explain to me later why they test things under 16G, because I don't think any of us would survive 16G, but it is one of the requirements that you actually do this. And in the next slide, you can see it in place. You can see the thing in place, and in the next slide, you can see the metal printed parts coming out of the commercial metal 3D printer. Now, let me just move on to one thing that I've noticed with all this generative design, and I'm happy to talk about this idea because I think it's somewhat frightening, somewhat misunderstood, and somewhat confusing what generative design is. And so I'm happy to talk about it. But one of the things that often comes about are these parts that are difficult to fabricate in traditional ways, and more often they're best fabricated with additive manufacturing and 3D printing just because of the complexity of the geometry. So it's great for if you're Airbus that you can actually print these parts on machines that cost $250,000 or $500,000. But I started working on a 3D printer because I thought there might be a way to do metal 3D printing for much less. And so in the next picture, the next image, you can see these are all prints that came out of my homemade metal 3D printer. So this metal 3D printer, I think, is a perfect Fab Lab project. It is made from a computer-controlled gantry, and a MIG welder. This is a MIG welder you could buy at the local hardware store, and the gantry you could build out of standard parts. Many people at Fab Labs have built similar kinds of mechanisms. So the quality of it is getting really quite good. At some point, probably this summer or into the fall, I'll publish some open source plans for it, and I'll put the models up in the Fusion Gallery so everybody can get access to it. But so far, we're having really good success. And the cool thing about this 3D printer is not only does it prints anything you can put in a MIG welder. So far I've done steel, bronze, and aluminum. But I think you could also print a number of other materials, and it's incredibly quick. And so that little closed-shaped vessel, it's probably about 8 inches, maybe 10 inches tall. What's cool about it is that thing prints in about 30 minutes. So it's faster than my plastic printers to get something out of steel. The second thing that's cool about this thing is on my gantry, I have 2 heads. So one is actually the MIG welder, and the other is a little mill so that I can cut away parts in case I need more precision or I need finished surfaces. And I think this interchange between the two is really interesting. Just want to wrap up here on 2 things, other things that I'm working on. One is if you could cue up the next video. This is a project we've been working on to get around that frustration of 3D printing being slow. And so this is a project that we're doing at Autodesk. It's called Project Escher, and it's really about doing 3D printing in parallel. So this is some work we've done to build a little control system that will allow you to print with, the typical kind of FDM print heads, but doing multiple ones. So you can take a big bed and you can divide it up, whether you have 3 heads or 30 heads, and dramatically increase the speed at which you can print. Because I've just spent too much time not only listening to little 3D printers go back and forth, but waiting for the prints to come out. And so somewhere in this video, I know it's probably a little bit choppy there, but you can start seeing a machine that we have that has kind of a dozen heads on it, going back and forth in overlapping regions and actually printing. And it's a really interesting development. Once again, we'll probably put this out there for the public, and hopefully someone will build some commercial versions of these and bring them to market for those who want to buy them, and others can build them. So let me just wrap up on the last slide that I was going to show, which was, I think there's a lot of interest in 3D printing, but I think, what we've seen, in the Fab Labs around the world and the other maker spaces that's so incredible is this new generation of being able to make, and I certainly started making, and I would guess Neil did too, before everything was controlled by microprocessors. And, when I look at the future of making, while I am still a huge fan of traditional techniques and tools because I think they're an incredibly important part, one of the things that has opened up is that we can now control all of these things. Just before we got on the air, I was talking to Neil about my new favorite tool, which is a CNC press brake. And I love this idea of combining the old with the new. The press brake I have in my shop is 135 tons, and so it is brute force, to the extreme. But the idea that you can delicately control all the things like the fences and the back gauge on it, with incredible precision and repeatability, also delights me. So I can go through a small job really easily. And one of the things for me, a lot of CNC stuff was really made to do huge volumes of stuff. It was thought about in the aerospace and the auto industry. But what I love, it's becoming accessible to all of us. And I can now make things that I could not make before, or certainly could not make easily. And so we're really repurposing this stuff that was intended for something completely different in a way that's, empowering, individuals and small teams. And that's what I'm excited about. And when you combine, the software I showed you with things like Fusion with the ability to actually really drive all these machines, it's an incredibly powerful thing. And all I could wish is I was 40 years younger and starting making out again, because there's just so many possibilities out there. So thanks, and now we can talk.
That's great. Thank you, Carl. So I'm going to start with a couple questions, but then let me open it up to encourage people through the chat to post questions. Your 16G is a really profound point. We've been working very closely on the research side with Airbus on how you fabricate the whole structure. And what's going on is the testers don't believe the modelers, and the modelers don't believe the fabricators. And so it's like markup. They each put in these margins.
Right.
And the resolution is you have to make the fabrication equivalent to the modeling and equivalent to the testing, which is a complete do-over of the whole end-to-end chain.
Yeah, it is interesting, because even during the process of doing that partition, Airbus gave us the specifications for it, and we got it to a certain point, and they said, could you make it lighter? And we said, probably not with the specification that you gave us. And they said, well, you know how we came up with the specification? We said, no. And they said, we built one many years ago, and then we tested it, and that's become the specification. Yeah. But there's no absolute requirement that it actually carries that load.
No, there's so much accreted. And so that then leads into, in the roadmap to the replicator, Fab Labs are currently going through the 2.0 transition, which is where you make a Fab Lab, you don't buy one. So Fab Labs make Fab Labs.
Oh, cool.
And that unpacks to lots of consequences. One I want to start with is in Fab Academy, as well as the research, we teach people to design PCBs, to write microcode, to do additive and subtractive, and they make these integrated systems. And they think of it as an integrated system, but the design tools still think about circuits, code, and manufacturing as unrelated operations.
Yeah.
Talk about your roadmap for connecting form and function.
Yeah, so I think that is one of the big shortcomings, because when you look at many of the things we're going to build in the future, it is some combination of electronics and software and mechanical things. Even something as simple as the GoKart that my teenager built is that combination of stuff, and particularly as it gets autonomous. And so it's interesting that we were able to, at the time, model it in Fusion and test out the steering mechanism, but we couldn't do the first thing about turning it on and making it go in a digital way. And so, so one of the things we've done, and I'll give you a little bit on the roadmap, we do have a number of tools to design circuits, but as you said, it's separate. So we have a product called 123D Circuits. It's great for doing little Arduino things and PCBs, and has a simulator built in, and so it's nice for that. What we're doing right now is we're building a professional version that will be integrated into Fusion and be available later this year. Because we see this all the time, and I think until you can simulate what your electronics and what your software do, this is a really incomplete tool chain, and they have to be together. And yeah, you'll get like immediately fast benefits, like everyone who does a PCB then says I need to make an enclosure. I think that's a little bit interesting. It's not nearly as interesting as really being able to simulate it. So later this year, you'll see the first integration of where you start seeing electromechanical devices being able to be designed and simulated together.
That's great. That's a crucial stumbling block. Then to two more going down that roadmap. As we move to Fab Labs making Fab Labs, I originally interpreted that as a machine making a machine, but what we're finding is you really need object-oriented hardware. So you have physical degrees of freedom that move, sense, and have end effectors that you compose into parts of machines with networks, with distributed computing, with software modules, and the whole thing is reconfigurable. And so it's sort of modular all the way down. And what it's beginning to do for us, and I'm curious how this reflects in what you're doing, is it's sort of blowing software apart. Instead of a CAD program, a CAM control program, a machine control program, you just have sort of things you can compose, so you can reconfigure the software to as you reconfigure the machine.
Yeah, so
And
I think it's...
sort of finish that. In a world of rapid prototyping machines, you sort of need to do rapid prototyping of the software to go with them. And so how do you think about that?
Yeah, so I think it's a really interesting idea, and I think there's this real tension between these independent chunks of code, as you point out, which are really necessary that you need to reconfigure, and yet if you push just down that way, you end up with 52 independent things. And that was kind of the workflow problem I described at the beginning. So the place where we're headed is trying to build a web-based, cloud-based platform of connected web services that you can tap into independently. So as an example, we don't pre-configure it, but for example, the CAM part of it, which generates toolpaths and other things, you can access through a web service. And so we're seeing this world emerging in which the new platform connects through web services, and you have dozens and dozens and dozens of microservices that you can use. One might translate from a CAD file to some other representation. One might generate toolpaths. One might do finite element analysis. And you can use all those things and pull them together in ways that we may have imagined, but more likely only you have imagined, and only you may specifically have that need. And so we just announced this platform called Forge, which is exactly that idea. And then even the things of where it shows up. It might show up on very conventional machines like Macs and PCs running in browsers, but someone may want to pipe it into a Linux machine, or into something running a Raspberry Pi, or even into my machine tools, and have some of that show up on the control. And so I think that's the interesting future.
So that's a great answer. Software is composition of these functions. I think it's hugely important. I first encountered that, and Tomas, before you talk, there's an echo on your side. So, yeah, thanks. I first encountered that. One of my favorite Haystack Mountain and Crafts.
Hold on, you cut out there, Neil.
Yeah. So one of my favorite Fab Labs is Haystack in Maine. Have you ever visited?
Yes, I have.
Yeah. So, and we went there with the machines and all the best practices software, and all the artists and craftsmen there would take every single tool we had that did anything and use it backwards and upside and inside out, and want to do the workflow in the complete opposite direction. And it really spiraled into giving up on this idea of a program and instead just sort of blowing apart things you compose to solve a problem. Yeah,
so that's why I said there's this interesting tension in that you want to blow it apart, but then sometimes you look at these workflows and you go, even to get something 3D printed, people go through 7 pieces of software. And right. I think it's fine for a one-off, but those of us who have built enough, I cannot stand, after I've designed everything, and let's say I cut it out on the water jet and it's wrong, so I have to go back and do it again. The first time's fun, the second time is sometimes necessary, the third time is just totally annoying. And that's why we need a better way to keep this stuff together. We've done the similar thing, Neil, down at Pier 9, the digital fab facility that I showed you. We have this artist in residence program there, and one of the reasons is for the same reason as Haystack. We have 30 artists in residence, and I would say, not only do they break the rules, they don't even pay attention to the rules. It's just they have something in their mind they want to create, and it's been incredibly informative in kind of going, the software needs to be way more flexible, and kind of conform more to what they want to do, as opposed to we've often, those of us who've built software, have asked the users to learn what the software wants to do.
Right.
So I think that's a great model.
One more general question, then we'll go on to others. How do you think about complexity? So I know you have, and we've been working very closely on things like whole genome design. And what's interesting about that is you don't specify 5 fingers, you specify a developmental program.
Yeah.
And you don't design a billion transistor IC with a GUI.
Right.
It's this very abstracted representation. So assume success in everything we just talked about for the last 10 minutes. How do you then think about exponential complexity?
Yeah, so the thing that we're trying really hard is with this, experimental research project called Dreamcatcher, which really is just a framework. And, so that's where the heat exchanger and some of the work with Airbus was done. And there's some very, out in the future kind of projects being done. And you're absolutely right. This idea that you're going to use a user interface to model and, do high school geometry is completely wrong-headed. It's completely backwards. As a matter of fact, it's not only wrong for dealing with complexity, it actually, for most engineering problems, is probably the wrong end to start at. Before you know whether or not you've actually solved the problem or are well on the way to solving the problem, you're doing kind of low-level geometry operations. You're asked to sketch things and extrude things, and you're working at the wrong, I would say, level of abstraction for the problem that you're trying to solve. And so for my thing is, one is, I think, on general problems that of manageable scale, we need to give people tools that start at the right side of the problem instead of the wrong side of the problem. And for these super big complex problems, like that heat exchanger, I don't think anyone would have ever gotten to that answer, both in terms of shape complexity and near optimal thermal performance, if it hadn't been for the computer doing it. Now, you think about this thing, that thing probably took 100,000 CPU hours to compute. And so on one hand, it sounds crazy, but remember, the price is coming down, and at today's prices, that's $2,000 or $3,000. So for a manufacturer to spend $2,000 or $3,000 for a near optimal design, that's reasonable. And so this is just the first step in building this general purpose framework in which you can plug in things, and we built it so that certain kinds of solvers, understanding finite elements, for linear and nonlinear stress, understanding computational fluid dynamics, we build in. But there are other kinds of properties that we're not even trying to, and we're allowing others to plug in their own analysis tools and allow it to send this off to thousands of computers to compute, and then have a bunch of different optimization techniques to get to a better answer. And so I think if we want to deal with complexity, the only possible answer we have is computing power.
Okay. So there's a question about your new Boston facility, about what'll be there and how people can get access to it. Maybe warm up by describing Pier 9 and then talk about the Boston.
Yeah. So I can tell you a whole lot about more about Pier 9. So Pier 9 is a facility that we built down on the waterfront in San Francisco. We built it about 3 years ago, and it has some office space, but it's primarily a digital fabrication facility. And in it we have water jets and welders and CNC machines and dozens of 3D printers. We also have some work that we're doing, some research work on working with industrial robots there and trying to use industrial robots instead of for mass production, for one-off jobs in which we talk and robots visually identify stuff. So it's this huge facility. It's on the waterfront. It's right next to one of the world's great museums, the Exploratorium. And so it's the next pier over from the Exploratorium. And the things we do in there is, number one is we test our software there. We also have the Artist in Residence program I talked about. The team that does Instructables works out of that office. And we also do some partnerships with companies and people in the community. So we have a number of people who come in there and use the facility, and we've worked with the community on a whole bunch of stuff. So that's what it's been hugely successful. It's also it's available to all the Autodesk employees. So Autodesk employees can use it as their shop. We have a big office in Boston, and we're just opening it. I haven't been there yet. I need to get there this summer. But we're opening a similar facility, and I would say the difference is certainly we've learned and we've modeled a lot of the Boston facility after Pure 9. The slight difference in orientation is most of the stuff in Pure 9 is kind of product-size stuff. So things like a GoKart would be an appropriate scale. The stuff in the Boston office is intended to be more on architectural scale. And so there's more space, and some of the tools are larger capacity, so we could do some things in the built environment instead of, around products. I don't know much more about the programs. There's a bunch of people, and through our connection, we can get people information about what's going to actually go there. But I don't know what programs are there yet, and how we're going to work with the community there. So I'll find out when we go this summer.
I think you'll find great things. I was just management of GE in Boston on their move.
Oh yeah.
And they had a really interesting comment about sort of all that consumer stuff was fine, but what we're going to do here is the really hard stuff, not that kind of easy consumer stuff. So I think you'll find really great alignment. Well, Tomas, go ahead.
Yeah, well, thank you very much, Carl, for all the presentation. I just wanted to make maybe 3 questions in one, very quick. The first part of the question is...
sorry, I hate to do this, but I have to do it. Sorry. Ooh. Sorry, it's breaking up. Tomas, I hate to do this, but just since Carl doesn't know you as well, to warm up Carl on you, could you explain the Fab City Project to Carl?
Okay, Carl, I'm coordinating the global Fab City Project, which is aiming to bring the Fab Lab impact to the city scale, trying to reduce the amount of things that city imports and actually keep the atoms within the city limits, and just making data travel around the world. So we're aiming for a future in which shipping containers are not longer existing, but actually people is sharing data and files on how things are made. That's connected with the question, actually, thank you, which is, I will start backwards. One is like, what is the sustainability agenda and bringing software design tools for people? And if you think these software design tools are going to be as important as writing, is this part of a new literacy?
Okay, I think I got most of your question. Broke up a little bit there, Tomas. But one of the things that I think is important about sustainability is, in the simple context, is giving people the tools to understand the implications of their design choices. Right now, many people don't have the tools to do that. And if you think about within the city, things like buildings, if you asked many architects or engineers, if I took a building and I rotated on the site, would it consume more or less energy? Many architects couldn't answer that question about the building they just designed. And what I think we need are design tools that give people instant feedback on questions about energy usage or material usage, and to do 2 things. One, to be the guardrails as you're designing, but secondly, to build experience and intuition over time. So you realize every time you change this, that the energy consumption goes up, you realize you're in kind of a bad part of the solution space. And I think it's a really important thing that's been overlooked. And many people don't really understand the implications of many of the design choices on questions like sustainability.
The second part of the question
Bad dropout.
Education.
But Tomas, we're not getting that.
And
I don't know if you
if
can
you
move your
think
location or talk really slowly, but bad dropout.
design tools are going to resist. Oh, sorry. I have bad connection from the airport.
Try again, maybe slower, or
Question.
I don't know if you can change your location.
Can you hear me now?
Yeah.
Yes.
Yeah. So the second part of the question was about the software tools or design as a new literacy for the future of education. How do you see that? If it's going to be as important as writing to use design tools in your software?
Well, I would start with the broad question first, which is one of the things I'm thrilled seeing both in high schools and colleges around, certainly the United States, but on a worldwide basis, is just the basic ideas of computing are becoming, faculty and administration are realizing that it's as important as some of the other, as reading and writing. And there are now freshman introductory computing classes, and in some colleges in the U.S. they're becoming a required part of the curriculum. So I think for people to go forward, and regardless of the domain they're operating in, the ideas that underlie computing are essential for that. I think there's a new generation of design and engineering tools coming, as we get to stuff more specific to the stuff we're interested in. I don't think everyone's going to become a designer or a problem solver. It's not in everyone. But for those who do, and there are many more who are capable than do it today, I think we need a new set of tools. And, truthfully, that's why we went out and we built, Fusion. I mean, it was amazing to me. I went around to, great engineering colleges around the U.S. and would talk to them. And I would look, and the thing that would amaze me is that despite all the great intentions and the access to this new technology and more hands-on approach to learning, most of the schools were teaching people software that was designed before the students were born. And it just seemed wrong to me. It'd be like, okay, you just got into MIT. Here's a 25-year-old cell phone. At MIT, you would do it to take it apart, but not to use it. And and so for me, that's what I saw was just this, slow adoption and stubbornness, in schools to move to new things and to really teach what I consider to be really out-of-date technology. And so when I look at the software tool, said there was the world has changed substantially in terms of what we're capable of from a computing point of view. It's changed in terms of the devices that we want it on. It's changed in terms of how much we expect to collaborate on projects, and we needed a new generation of software to address those needs.
Thank you. That's all for me. Neil?
Okay. And so just to unpack Tomas's quick description, with his colleague Vicente Gallart, who started the Barcelona Fab Lab, Vicente became the city architect of Barcelona, and their buddy Trias became the mayor. And the connection was great design sense, 50% youth unemployment, whole economy broken.
Right.
But they would buy crap from ships in the harbor, and trash trucks would go out to trash dumps. So they considered the city a product in, trash out conversion device. and they instead wanted to make it a data in, data out. The atoms stay, but the bits go. And so they started putting Fab Labs all around the city, only secondarily for businesses. The primary reason was urban infrastructure. In the same way it provides electricity and clean water, it provides the means to make as infrastructure of the city. 2 years ago, when all these labs met, Barcelona's mayor pushed a button to start a 40-year countdown to urban self-sufficiency. So food, energy, everything they consume is created locally. Last summer, the leadership of Boston, Somerville, and Cambridge joined that commitment. This summer, all the labs are meeting in Shenzhen, where the whole manufacturing ecosystem is pivoting to personal manufacturing. And what's emerging is, in many ways, cities as the ultimate realization of the whole Fab Lab maker story of equipping cities to produce what they consume. So Tomas is now coordinating this growing global group of cities that needs this amazing technology base. The goal is 1% in 1 year, ending in 40 years with self-sufficient cities.
That's fantastic. Have you talked to anyone in San Francisco yet? We need to do something there.
That's a good question. Let's see. I talked to your previous mayor as this was emerging. I don't think we've had any contact with the current city leadership.
We can help there. It sounds like a great idea. You know, it sounds like awesome work you're doing, and I've heard about what's going in Barcelona. I just never got the opportunity to meet any of the people responsible. So this is a pleasure for me as well.
So anytime anybody says city or making, there's this Fab City Project, because you need this huge technology base to do it that no one city can do. And so that's what Tomas is coordinating.
That's great. And we should probably figure out a way to look at what we're doing in Boston, because the emphasis there is really on urban infrastructure more so than product design.
Yeah, I've been up to my ears with smart city stuff that always is like sensors and big data, not actually physically changing the whole life cycle of the physical form of the city. Yeah, absolutely. There's a note online, Zuberi is just praising you for this focus on end user and craftsmen. And I wanted to note my interpretation of Carl's management style is he does it very selfishly. He gave the explanation of Fusion 360. That's not right. He did it because he wanted it.
Yes.
End user, he was educated, he wanted it. And he gave the explanation of Pure 9, but that wasn't really right. It was because he wanted, as sort of massive self-interest, he pivots the company. And I think it's a management technique.
I think it's a keen observation on your part. Massive enlightened self-interest has done good things in the world, and you know what? There's a part of truth in it. But like, for example, I'll give you a great example with this. Like when we started making Fusion and we put CAM in there, which is, you know, the CAM kernel and HSM works and stuff like that. One of the things that bothered me was CAM historically had only been subtractive manufacturing, like CNC machine tools. And I said, what I often do is I cut it on the plasma cutter or the water jet or something. Why do we have a different set of tools for that? And why do we have a different set of tools for driving CNC press brakes? We should be able to do it in one place, because as a user, I don't need 25 pieces of software and then 25 machine tools, all with their own controller software, because I'm an intermittent user. These things were designed for people who work 40 hours a week in front of that machine. I use it intensely for 8 hours on Saturday, but I may not get back to it for 2 weeks. And so I said, no, I want a whole different thing. And so there is a bunch of selfish interest in here, but hopefully other people find themselves in the same position I do. So at least my self-interest is well intended.
Let's see. Sarah is asking about schools integrating. There's a lot of interest in coding. We talked a bit about that. One of the things I wanted to note about her question about CAD, CAM, and fabrication in schools is we backed into doing the Fab Academy. We tried to partner with local schools when young kids would learn, you know, all these skills and go way ahead of local opportunity. And we consistently went off the rails because the schools would sort of hijack and turn it into whatever they were doing. So we started this Fab Academy network to teach it using the whole network as the campus. We then went to the accreditors and they said, we love this. Where are you located? And we said, Earth. And they kind of shrugged, because accreditation by law is geographical. You accredit the physical place, not the network. But they said something useful. They said pretend. Right. Make up a credential, but let it have teeth by students building skills-based portfolio, and eventually we'll catch up to you. And interestingly, the one question we never get is who accredited the Fab Academy, because nobody knows how to accredit it. They want to know what the students know how to do. Right. So for me, what's interesting is, in Sarah's question, is to really meet the educational impact. Part of it is turning into reinventing how schools work. There's a lot of assumptions based into what a school is that don't really fit this world that we're creating. You know, is that something you're running into?
Yeah, I mean, we ran into the same thing, and we see this really broad. I mean, the good news is, the really optimistic part is that schools all over the world, from secondary schools to universities, are rethinking their curriculum, and they are going, to more skills-based things across the spectrum. But we also find the same thing of it's all over the place in terms of what they actually want to do. But I can think of, public middle school in England I visited, and places in Asia that are doing what I think is, kind of the best kind of work. The other thing we're trying to do, and I think it's great that there's, Fab Labs and there's information, because one of the things we find is a ton of people with interest, but not enough curriculum and other things to go to the next step. So, it's the single teacher in North Dakota who wakes up and says, this is the greatest idea, and then they figure out, through a bake sale how to get a 3D printer and a something else, but they don't know what to do next. And so that's where I think, the real power of Fab Lab and Fab Academy, and so we've provided a fair amount of curriculum, just because I think we're now at that stage of people have gotten the basic, and we need to give people the tools to get to the next level. But the thing that I keep seeing, and as you talked about, in the size of the network and how it keeps doubling, is that the interest is real. It reminds me a bunch of years ago, and I was talking to Bill Gates about this with someone, and and we were talking about the maker movement, and he was totally dismissive of it, and it was interesting, because I said, look, this is just like the homebrew computer club, and what it gave rise to. We were at the very beginning, and yes, just like the homebrew computer club wasn't the first one to make a computer. IBM existed long before the homebrew computer club. This is actually making, and more importantly, solving problems to a completely different and much broader audience than you ever imagined it was interesting for. So it was interesting how dismissive people who are, otherwise very smart can be of this thing. But you guys are proving every day that it has, many more legs than imagined.
Yeah. So let's end with this question. Anders is asking, we already assume everything we just talked about. He's saying, what's the big picture future for all of these tools? So, assume all of this is the warm-up. What's the big picture future?
There's a future that's interesting, but a little bit scary. Because at a certain point, you can remove the people from the equation to some degree. And the question is, what does the world look like when we remove the person from this problem? Like right now, what we're doing is we're just getting more leverage through software over these things. But, I don't know what the world looks like when you get to a degree of automation that, for example, the person describes that requirements for that heat exchanger, and the heat exchanger pops out the other side. So imagine the automat for made goods. You just type in your requirements, and you come back, and the door opens, and here comes your heat exchanger. And I'm not incredibly fond of it, but we keep putting one foot in front of the other that gets us a little closer to it. I don't think I don't think that dark picture will actually exist, because I think we as humans, put the value in of what's important and what's not important. And there are things that we do really well, which is why we're doing that work of seeing how cooperative work with robots really works. But there is a big picture future where we do have to think about this. And just as the problem described, that was the impetus for doing stuff in Barcelona, I do worry about each time we encode things in software and we leave less room for people to actually do work.
So let me give you an optimistic version of that related to the Fab Lab network. For the UN General Assembly, where they launched the Sustainable Development Goals, which was the biggest gathering of heads of state ever, we worked with the White House to run a Fab Lab at the UN, and the reason was they wanted to show not just goals but solutions. And Beno Juarez, who was trained at Barcelona and runs the Lima Fab Lab, he grew up in the Amazon jungle, and he said when he was a child, your choices were farmer, soldier, or terrorist were the three things you could pick. And now he's sending rapid prototyping up the Amazon for sustainable production in indigenous communities. And what happened at the UN General Assembly is these sustainable development goals are things like clean water, education, shelter. And if you look at them, every one of them, it turns out, rests on access to digital fabrication.
Yep.
And so there's this epiphany moment of all the diplomats, sort of this light bulb going off of like, first, why are you here? And then realizing sort of the future of world development is universal access to these tools.
Yeah, no, I generally speaking have a much more optimistic view that says, look, these are the tools by which we solve important problems. And we're empowering millions more people that never had access to it. You know, in the world we grew up in, you know, these problems were outsourced to large companies. And what we're finding out is that there are millions of people who can now contribute, and in many ways with more innovative and more creative answers. And so the more people we train to think this way, that they can solve problems, you know, it's fantastic. It was like I said, with, you know, where we started with like Willie and the GoKart, that moment at which you get that creative confidence that says, I can get from idea to thing, and I can get from, you know, problem to solution, is an incredible thing. And so the more people we train to do that, the better off the world will be.
That's great. So with 1,000 Fab Labs, there's one anywhere you go, and I'm sure they'd all be delighted to host you. So
I visited quite a few, but I haven't seen them all.
Okay.
So, great.
That's great. This was a pleasure. Thank you, Carl.
Thanks, Neil. Bye.
Bye-bye.
Thank you, Mas.
Thank you, Carl. Thank you, everyone.